So today, this is the first, we have a wonderful seminar series for the Beaver Summer Institute. We have 18 speakers. Today is the first day. It is my pleasure to introduce Professor Paulo Lozano. But before that, one of the things we do is that we always say hello to him. So I'm going to choreograph this. In my count, we're going to say, good morning, Professor Paulo Lozano. Okay? Okay. 1, 2, 3.
Good morning, Professor Paulo Lozano.
Okay, thank you.
Good morning.
Okay, so I'll do the quick introductions. I'm not going to introduce the vice. I'm going to tell him something about him. Not in the was not in the abstract. So in addition to doing a wonderful research work you're going to hear about, he is also director of the MIT's MISTI Mexico program. And MISTI stands for MIT International Science and Technology Initiative. And he's also sponsoring 12 students from Mexico who's working on, I think, 2 race cars, right? And they're sort of doing this program on their own with a little bit of our help. And they plan to be here for the final competition and challenge our race car teams. Raise your hand, race car teams. All right, so it was, I think, Professor Paulo is actually sponsoring them. Second, next year we are discussing with him maybe adding another project where actually the small team of the students, like you will actually build a Cubesat, and then hopefully we'll get a ride to space, right? And some maybe a year later. And so I think there's a great opportunity for the students next year to work on a real Cubesat that actually will be in space. So with a little logo that's BWSI.
Absolutely.
All right, so with that, Paulo.
Thank you, Bob. How's everybody? Excellent. You like this summer activity? I think it's nice and different, right? I hope you guys learn a lot and contribute a lot to all these things and meet a lot of interesting people. So this is going to be the first one, right? I suppose the first seminar of the summer. So I hope I don't make a bad example to begin with. This is the title of my talk, right? I'm going to be talking about really tiny engines for really tiny spacecraft. And hopefully at the end of the talk, I will have conveyed to you the reasons why I think this is something that many of you as high schoolers and many people in school in general will be able to use to actually explore and use space. So let's get started, all right? The first question that I have is if you remember, well, you're too young to remember, but many years ago, several decades ago, if you think about a computer, a personal computer, that would be something that you never heard of, right? So this is the thing that Steve Jobs and Bill Gates always told us, right? Personal computers did not exist. Personal computers were actually just computers, which were big machines that fill up entire rooms, right? Nowadays, things have changed. You have all that computational power that you had before in a full room of computers, you have that in your pocket. That's a tremendous achievement of miniaturization of microelectronic devices. The invention of the semiconductor and many things that enabled putting a lot of technology in very, very small packages. And of course, the introduction of those little devices has changed dramatically the way we study, the way we explore the world, the way we communicate with each other, the way we navigate around the world. Everything has changed because of these little devices, right? And not only this, but the computation power that is embedded in many devices, like for example, the race car that you're going to be using in this summer. And we believe that something very similar is going to happen in space, the final frontier, right? I think that's very cool. What do we do right now to explore and use space? We have these very large machines. You can see there's a person or 2 people actually in there. Big satellite. This is a communication satellite. These are big antennas that are going to be pointing to the Earth. This satellite is going to be launched in a geosynchronous orbit. Do you know what a geosynchronous orbit is? It's basically the satellite is so far away that rotates around the Earth once every day, right? Synchronous with the rotation of the Earth. So the satellite appears to be stationary on the sky. And that's very useful for telecommunication purposes, right? So you send a signal to the satellite beams back that signal, bounces it back, and allows you to communicate from one side of the hemisphere to the other side of the hemisphere, well, as long as the satellite is looking at that. But this is what we're doing now. And what we think is in the future, actually things are going to become much smaller. Again, driven by the miniaturization of many components. A lot of technologies that happen to be invented because people like you actually went to school and studied chemistry, physics, microelectronics, nanotechnology, all these engineering areas, and also the application areas, business and so on. So you have actually a purpose for these little devices. Now, you can see the dramatic difference between these two concepts, right? These things are thousands of kilograms, thousands of watts of power. These things are about 1 kilogram, perhaps a few watts of power. And the key here is, can we make these things as capable as the big ones, in the same way as we made now, your portable phone as capable of those big computers of the past? And the answer is maybe. This is just happening, right? This is a revolution that is happening as we speak. However, these little satellites are becoming very, very popular. This is just a histogram showing you by year the number of launches of small satellites into space. So you can see that back in 2009 there were relatively few launches of small satellites, right, into space, and this has been growing tremendously. And now this was a projection that was made by this a consulting firm, Spacework, in 2014. So the data for 2014 wasn't finished, and obviously these are projections, right? Very optimistic and somewhat not as optimistic projections of the launch of these little satellites. Of course, now we have the data for 2014 and 15. It's actually there. So even the most optimistic predictions of the number of satellites, of small satellites that are launched in space, are being beaten by reality. The actual numbers are much higher. So this is a revolution that is happening. I mean, it's an exponential behavior, and whenever you see an exponential behavior in things like this, or in physics, or whatever, it's because something is happening very quickly, right? You know about that. What are the applications for satellites in general, and the potential applications that little satellites can have? Well, these are the applications that satellites currently have, like in communications, right? Your TV communications, high bandwidth communications, navigation like the GPS satellites, science, you want to observe the behavior of particles in the higher atmosphere of the Earth, weather, if you're observing down and looking at storms on the Earth, imaging, taking pictures of the natural resources, or traffic, or cities, and it's very important. National security, making everybody safe. Exploration, sending probes to the planets, right? Observing very close what's going on with the different parts of our solar system. Debris mitigation, being responsible citizens. Well, we put a lot of stuff in space. We make sure that we are able to bring that stuff back. Education. So we have a group of students in here. Potentially next year we can build a satellite. That's part of the educational activity. And this is the one that I like the most. The new applications that can come up once these things are becoming so popular that high schoolers can actually build their own satellite and put it into space. What for? You can only think that the possibilities are endless, right? The sky literally here it's not the limit, actually. You can go to space. So you can build constellations of satellites around the Earth and providing these services. There are a whole bunch of startups being founded very recently that are trying to exploit this new paradigm of space use and exploration. Now, this is the first time in history that actually startups are being founded on space technology and space science. This is unheard of, right? So many of these. I mean, a few years back, startups only were happening in the technology field, like apps for your phone, or software, or niche markets in microelectronics and so on, or some consumer devices. But for the first time, we're building stuff that goes into space, and actually little companies are interested in doing that. And a lot of that activity is happening at school, in different universities, different labs. Now part of your laboratory is actually to build tiny little satellites. You can see a few examples in here. This is one that I like a lot, in which they just took a phone, a smartphone, put it inside the structure of a satellite and put it in space, and actually it worked. This was put in space by NASA Ames. However, there are challenges in miniaturization. We can do a lot in microelectronics, but there are challenges in power and thermal, so how much power we can actually handle in these little devices. Communications is very hard to communicate back and forth from these devices. And propulsion. So far, they are unable to move once they are in space. These are key challenges, and I think that propulsion is going to be one of the key enablers. Now, if you are allowing these things to move once they reach their orbits and change their orbits, go to different places in the solar system, then you're going to really change the future of these technologies. So, we're going to be talking about space propulsion. So this is lecture number 1, right? Don't worry, this is the only slide I have equations, right? But, I mean, we are engineers. We have to have equations, at least in one slide. We're solving the equation for a rocket, right? The rocket is a mass variable system. You have heard of Newton's laws, of course, right? F equals ma. But in this case of a rocket, the m, the mass, is changing with time, right? So we cannot integrate as easily as you do when m is constant. So for example, when you solve Newton's laws for a rock, and the rock is not shedding mass, then that's fine, that's very easy. But the rocket is actually, you know, is ejecting mass, so the mass of the rocket is decreasing, and its velocity is increasing. So it's a mass variable system. Anyway, we won't go through the math, but you get a nice exponential in here of the final mass depending on the initial mass, right? So this exponential behavior says that any changes on the coefficients in here are going to produce a dramatic change of the final mass that you can get once you accomplish your goal. What is your goal? To accelerate your rocket and increase the velocity by this quantity that we call delta V, the increase of velocity of the rocket. And what is C? That's the exhaust velocity. That's the gases coming out of the rocket motor, and they accelerate to some velocity. That's this velocity C, right? Now, the problem in here is that if this delta V is large and this C is small, that means that this ratio in here is going to be relatively large, and the exponential of the negative of a large number is very small. So that means that if you have some initial mass, say 100 tons, you are going to end up with a tiny little mass as your final mass. And this is the reason why rockets are huge and the payloads are really tiny, just at the tip of the rocket. There's nothing we can do about that. You can associate this velocity to energy. You make an energy balance. So the more energy you have in the substance, the higher the velocity is going to be able to achieve. That kind of makes sense, no? There are two ways we can inject energy into an exhaust of a rocket. One is chemical, burning stuff, which is the way that currently is done, and the other way is electric, right? So, interestingly, chemical rockets are limited by the amount of energy they can put in the exhaust. And electric engines, they are not limited by that. You can put as much energy as you want on a particle by electrical means. We can talk a little bit more about that if you want, but it's an order of magnitude difference in velocity, in exhaust velocity, if you use electric motors compared to chemical motors. And what is the difference? Well, say that you have two identical satellites. One has chemical rockets and the other one has electric thrusters, right? And the purpose is to accelerate these two satellites to the same final velocity. So both of these satellites are going to achieve a change in velocity delta V. Okay? So the chemical exhaust is going to move much slower than the electric exhaust. And just by doing the momentum balance, it turns out that you need much more fuel in the chemical rocket than you need in the electrical rocket to perform the same mission. So there are a little bit of subtleties in here, but the fact is that you have much more room in here to put useful stuff as opposed to just have fuel. And that actually is very good for little satellites, because what you want to save in little satellites is precisely room. You don't want to put a lot of fuel in your little satellites. You have very little volume to begin with. Okay? There are many types of electric propulsion thrusters for big satellites that have been tested in the past. Ion engines and Hall thrusters. I have an ion engine in here we can talk about if you want at the end of the lecture. I have a Hall thruster in here, which is actually the smallest Hall thruster in the world. It's pretty bad efficiency. It's very hard to miniaturize. And this is an application, for example, of ion engines. This is the NASA mission Dawn that is visiting asteroids. It visited asteroid Vesta, now it's around Ceres. And the key here is that if you insisted, and instead of having these nice electric engines on this satellite to perform this mission, you insisted and used chemical rockets, then for this wet mass, this is actually the mass of the satellite, if you use chemical, the mass of your satellite during launch would have been 26,000 kilograms. You cannot put 26,000 kilograms with any rocket right now, so it's out of the question. But instead, using electric thrusters, the mass is just this, wet, which means contains the propellant. So it's great. We can perform very interesting missions. This probe has gone to Ceres. This is an image of Ceres. This is one of the craters in this planetary body. And they discovered these deposits of salt in here that have amazed scientists. So we're making a lot of discoveries thanks to this kind of technology. Now, any electric propulsion engine is just like a black box, all right? Inside the black box, we have several things. We have ways of producing charge. We have ways of accelerating the charge. This charge is coming from a propellant that is injected, and everything is hooked by power. All of these things need to be miniaturized for us to put it in a small satellite. Now, the question is there an alternative for tiny little satellites? And this is the work that we have been doing at MIT for the last few years. So let me just illustrate this. Very simple terms. We still need a propellant. So this is our propellant. Now, the propellant is composed of exclusively positive and negatively charged species. So these are ions that are in this propellant. It's a liquid composed of only positive and negative ions. And then here comes the magic trick. We're going to take some atomic-sized tweezers. We're going to extract each one of these ions one at a time, apply an electric field, accelerate it. There you go. We have a rocket. And you see these are ions, so this is at the atomic scale. So it's extremely small. It's perfect for CubeSats and for small satellites. It's really small. If anything, we're in the trouble of actually scaling this up to macroscopic dimensions so we can actually handle it, right? Now, of course, this is the illustration. In reality, we have to do this another way. The way we do it is we have what we call an emitter, which is it's just a sharp needle. This is a tungsten needle which has been electrochemically treated to be wetted by this magic substance that is composed of only positive and negative ions. We apply to that emitter a high voltage with respect to what we call an extractor, which is just a plate with a hole. That sets a very strong electric field at the tip of this needle, right? And the liquid becomes unstable under this very strong electric field, and the liquid collapses into a very sharp liquid structure known as a Taylor cone. And at the apex of this cone, the electric fields turn out to be billions of volts per meter. Very, very strong. And is so strong that actually the ions can be extracted and fly away and then are accelerated into space and provide thrust. So there is scientific evidence, measurements in other laboratories, in my laboratory. Back in the day when we were discussing who discovered this first, it turns out that we discovered it at the same time. Very exciting times, 2003, 2004. Anyway, you can see the gap between actually making the scientific discovery and applying in an engineering device. We're in 2017. The first thrusters with this technology flew in 2015. So there is a relatively wide gap between having an idea and then making it happen in complex systems like this. This is the magic sauce, right? So the liquid that is composed of only positive ions and negative ions. They are molten salts. So think about table salt, sodium chloride, right? That's solid. You eat in your salad. And if you wanted to make it liquid, you dissolve it in water or something. But there are a group of salts that are liquid at room temperature. And the difference is instead of being monoatomic, like sodium chloride, these are composed of very complicated molecules, organic and inorganic molecules, very unsymmetric. They are so ugly, they cannot get organized into crystals at decent temperatures. You need to go to really low temperatures for them to organize, right? So they are poorly coordinated, as chemistry people like to say. But they are ideal for us because they are composed of only this positive. In this case, this is the positive, this is the negative. The name of this is 1-ethyl 3-methyl-imidazolium tetrafluoroborate. There you go. They have zero vapor pressure. So you can expose them to the vacuum of space and they won't evaporate. Why are they have zero? I mean, if you put water in space, it will boil, right? Because the bond between water molecules is a van der Waals bond, which is very, very weak. These are neutral species, and the only bond is through the dynamic dipole, if you know what is that, right? It's very weak. But in this case, this is positively charged and negatively charged. These are Coulomb interactions. Very strong electric fields trying to keep these things together. Okay? So that's why they don't like to be evaporated, unless you apply 1 billion volts per meter, which is what we do to these poor guys in order for them to actually be extracted as single ions. They are safe, non-reactive. They are salts. You can put them on your salad. No, don't do that. But in principle, you should be able to do that. And this allows us to put all these devices in a very compact package. This is the design, right? So we drew this in the blackboard. This is what we want. We want the propellant in here to infuse a substrate. It's a porous substrate, so it's like a foam, and the liquid, goes through this foam. We build tiny little tips on this foam, and from each one of these tips, an ion beam will go and produce thrust. So this was in the blackboard back in 2006, 2007, and we said, let's build it. Next month we'll have it. Yeah, right. But we were able to do it, right? This is a scanning electron microscope image of these tips that we built. These are built in porous glass using laser ablation. So we go Star Wars on this, right? So we aim a laser on the substrate and we etch the tips one by one. It's a process that we have been able to control quite well. You can see the tips look very nice. We have these arrays. We have about 500 tips in 1 square centimeter. Each one of them will produce an ion beam. Why do we need so many? Well, because each one of them will produce very little thrust. And in order for us to get more thrust, we put more needles, right? And this is how it looks like. It's a device that is packaged using MEMS techniques, the same techniques that are used in the semiconductor industry to package microchips. Inside of this microchip, we have that porous glass material with the tips. Each tip has an aperture in front of it, the extractor. You remember that plate that we apply the electric field to? And you can see the size is tiny. The size, not the cost. That's not the cost. It's the size, all right? So if you have a quarter, I cannot give you an engine right now, right? I have one of those engines in here, so you'll be able to see that. Yeah, I want you guys to come. You probably cannot even see it. It's inside this box. But yeah, absolutely. These two guys have the same performance, all right? So this is what miniaturization does. Right? And the propellant tank is in there. The propellant tank on this guy is not here. It wouldn't fit on this cart, right? Now, there are many different scales in here, so it's important to realize that many different disciplines come into the design of this type of devices, right? So we have a centimeter-based device and goes to the millimeter-based, micron-based, submicron-based, and nanometer-based, right? Where the ions are coming from. These are simulations. This is a fluid dynamic simulation of the meniscus of the liquid, and this is a molecular dynamic simulation of how the ions are extracted with this billion volts per meter. So these are real simulations. You see the ions. I'm living, and I'm producing thrust, yay. And then you feel the thrust to the left, right? But many different disciplines are required for this. We need physical chemistry to actually perform these simulations. We need nanotechnology to be able to do this. We need fluid dynamics to be able to, and electrohydrodynamics to actually being able to simulate these liquid structures, and engineering, of course, to design the devices in the first place. Okay. This is one of the devices with a propellant tank, and that is my hand just for reference. So we have enough propellant in this little tank to fire this engine for about 500 hours. So you see, it's very little amount of propellant, and will fire for a very long time. That's the benefit of having electric propulsion. This is an electric thruster, and you remember that we need very little propellant to achieve an interesting mission. It's very simple devices. Just mount them on the top of, of a board, an electronic board, and put it on your satellite, and then you can fire. And now, do they work? We did a very interesting experiment. We have a magnetically levitated Cubesat, which actually I brought one, right? I can magnetically levitate a Cubesat. Let's see if I can do this without embarrassing myself. All right, so this is what's happening in there. I have a CubeSat like this that is magnetically levitated, so it's not touching anything. No hands. All right, so we have that inside one of our vacuum facilities, and we fire the thrusters, and we make it spin around the axis, right? And it was wonderful to see this spinning, because if it's spinning, we're adding work to the system, we're adding energy, which means that in fact these things work. Because as a scientist, you always have to be critical of yourself, and don't believe anything just because you want to believe it. You have to have the evidence. I think that's evidence that actually is producing some force. And we have measured the force, and we have done that with this type of magnetically levitated balances. We send these thrusters to NASA. We send them to the Aerospace Corporation to do independent thrust measurements, and all of them match very nicely. So actually, it's pretty nice. Oh yeah, this is another application for these little CubeSats, and this is a demonstration we did last year, which I think is pretty cool. Same thing, we have a magnetically levitated CubeSat. Now the levitation is happening in here. We have this shaft in here. Keep it away from the magnetic field so that doesn't interfere with the satellite. Right? That's why we have that. Now in this test, we have a different number of thrusters, and we're able to control rotation around the axis in one direction or the other direction. So we're actually controlling the angular position of the satellite. So for example, in here we commanded the satellite to look at 0 degrees, right? And right now we're going to turn the thrusters off and see what happens. As you can see, this guy in here, right, is not perfectly balanced. There is some remnant rotation. So there is a perturbation always acting. So when the thrusters are acting, what they are trying to do is to counteract that perturbation. So we did that demonstration just to make sure that the thrusters were strong enough to counteract perturbations, because in space you will also have perturbations to fight against, like a very low intensity of atmospheric drag, maybe photonic pressure, other things like that. But anyway, this is the natural oscillation of those perturbations on the CubeSat. There's a fly, I can do it. And we're going to turn the controller back again in here and command the satellite to steer to 0 degrees. There's a little bit of an overshoot, and then we'll steer at 0 degrees. Now, why is this interesting? Well, we were able to hold this attitude, you can see the error in here, to about 10 arc seconds of an angle. You know what is an arc second? That's 1 degree divided by 3600, right? So it's very, very fine attitude control for little satellites. So this, this is one of the finest attitude controllers for small satellites. And what this enables you to do is to point your satellite to very small patches on the sky. For example, you can look at a star and collect light from the star. And even if you have a small telescope, collecting light for a long time, you will be able to see very interesting stuff on the sky. Like, for example, hunting for exosolar planets, right? Or looking at astrophysics phenomena, or laser communications. If you have another satellite and you want to point at the satellite with a laser, you can transmit a lot of information through a laser beam much faster than you can do with just radio waves, radio frequency communications. So laser communications in space is going to revolutionize the way we communicate. So you point the laser to another satellite. Imagine I'm the CubeSat, and that transponder in there is the other satellite. I'm pretty good with this. Yeah, I can aim at it. But imagine that this other satellite is actually 1,000 kilometers away. If I do, this jitter I have right now at 1,000 kilometers distance will be hundreds of kilometers off the other satellite. That's why I need something that precise to be able to really aim to the satellite and aim that laser so I can communicate with it. So it's challenging. We have done that for long times. This is a period of 10 hours, for example, where we actually held the satellite in such a configuration. Imagine it's talking to another satellite. Just 10 hours. What happened at the 10-hour mark? Why did it die? Well, it was just one satellite like this. We ran out of batteries. We didn't have enough battery inside the vacuum chamber. Anyway, it's interesting. We have produced devices like this for space flight. This is a project we did for NASA. We delivered these 3 units of, clusters of thrusters with the electronics. And we delivered this to the US government too. And some of them have flown. The first time they flew on May 20, 2015, we're biting our nails and watching this rocket go off and bringing some of our little satellites to space. And we verified that these little rockets actually can make the satellite move in space, which is pretty cool. And it's very cool because actually, since these devices are fabricated using MEMS technologies, we were able to put the names of students participating in the project. Right, Paulo? Yeah, your name is in there too. Yeah. All right. Now, what can you do with these kind of things, right? High delta V capabilities. You remember that mission to the asteroid, doing so much exploration and discovery in faraway places? What if we can actually do these kind of missions with little satellites? Can you imagine that thing? So we are developing right now something that looks like this. We call it the tile. It's basically just a glorified propellant tank with tiny little thruster chips. And we can put 2 of them on a little 3U Cubesat and still leave plenty of room for the payload and other spacecraft components. And with this, we have enough punch to actually, if they deliver us into a geostationary orbit, where the telecommunication satellites are, we can go all the way to the moon. It takes us a while because we have to spiral up, but in about 1 month, we'll be at the moon. Now imagine that, right? Imagine you students, your school project. What are you doing next summer? I'm going to the moon. All right, that sounds cool. What about a mission to an asteroid? Imagine taking one of these little satellites, again, the size of a loaf of bread or something like that, or a small backpack, right? Can you bring one of these to an asteroid? Why do you want to go to an asteroid? Well, there are many exciting things you can do in very small asteroids. So imagine if you bring your little satellite to a very small asteroid. It turns out that small asteroids, and by small, really small, I mean asteroids in the category between 5 to 15 meters in not really diameter because they have very odd shapes. These type of asteroids are extremely interesting. Why? Because hundreds and thousands of them actually cross the Earth's orbit every year, right? These are called near-Earth objects. From time to time, they hit the Earth. And when they do, they are actually, go into the news because it's big news, right? I don't know if you remember one of them a couple of years, 3 years ago or so, it hit somewhere in Russia. And it exploded in the upper atmosphere and destroyed, many windows and produced a little bit of damage and injury. So these are things that we have to be aware of. We have to investigate where they are. We have to investigate how they are built, right? Their composition, their topology, if we're going to actually deflect them at some point if they are going to pose danger. Because a 20-meter, 30-meter asteroid hitting a city will be a dramatic event, right? Normally they just explode over the oceans, over Siberia, and nobody cares. But if they explode over a populated area, that could be a dramatic thing. And we have the capability now to see them, and we have the capability to deflect them if we know their composition. So that's why exploring them is actually something that we should be doing. There are other reasons of going to asteroids. Mining, resources. Hey, why can you find an asteroid that is interesting? Well, when the solar system formed billions of years ago, heavy elements on the Earth went to the core, and lighter elements went to the crust. That kind of makes sense, right? When everything is kind of molten, gravity pulls the heavy species to the center, and the lighter stuff is left on the crust. So a lot of the interesting elements that we use in science and engineering and in jewelry, they are heavy elements, like gold, like platinum, many things like this, right? It's not that they are that rare overall. They are rare on the Earth because they are in the core. And we find very few of it in the crust. But if you go back in time to the time that the solar system was formed, which is basically visiting an asteroid, you find these elements just right there. Just pick them up. Oh, platinum. This is nice. All right. So there are companies actually who are looking at mining asteroids for their resources. You can find water on them. Water is great because that's also fuel, right, for chemical thrusters. So you can explore the solar system. And this is something that potentially you can do with tiny little satellites. For example, you can have that tiny satellite. It doesn't show very well, but you have it here. And if you're deployed around the geostationary orbit around the Earth with just 40 watts of power, again, 5 kilograms of mass, very difficult to communicate with, but that's another advancement that technology is making nowadays, autonomy. So many of these things will be autonomous. You don't need to talk to them. You deploy them, you put them in space, and you tell them, if you arrive to the asteroid, send me a beep. All right? So you send this here, this guy continues to thrust, and here's the moon. So we're going to ask the moon for a little ride. So it's a slingshot in the moon, and that's great because, there you go, slingshot. And that's good because we change the plane to the plane of the asteroid, and we gain a little bit of extra velocity, so we don't need that much thrust. And so we go back, and we're off into interplanetary space to boldly go. And it's too bad we cannot see very well, but the Earth is here, our NEO is there, and our interceptor is here, right? We call it interceptor just because it sounds cool. It's the Cubesat. And then it's approaching the NEO. And this mission would last on the order of 1 year. And about 7 months of that year, you'll be firing your thrusters. And how can you do that? Well, only with electric propulsion until you actually arrive to the thruster, to the asteroid. And you can do this because, again, you use electric propulsion thrusters that save a lot on propellant. So again, the sky is the limit. We can think about missions to go to the planets, have your little satellite and take it to Mars as long as you have propulsion. You still have to solve the issues about communications, right? Optical communications might be the solution in this. Relay stations located around the solar system, which potentially can also be deployed using little satellites. So it sounds like a lot of infrastructure to put in space, but remember, this is something that is enabled by the miniaturization of technologies, right? These things are by far less expensive than traditional satellites. If I wanted to send a big satellite into space right now, a typical telecommunication satellite, the cost of this is going to be measured in the hundreds of millions of dollars, right? And the cost of one mission with a CubeSat, that's measured, if it's really expensive, it's measured in the single-digit millions of dollars. So you're talking about a factor of 100 at least, right? Even cheaper. There are CubeSats that you can put in space for maybe 50K, like the one that very likely we'll do next year, or something like that. Anyway, I think this is my last slide, but I want to leave a little bit of time if we have. Maybe if you have any questions. I really thank you for your attention.
For like maybe 3 questions, so.
Yes.
Yeah, sorry. You said that it takes roughly a month to get to the moon. How much does like a combustion rocket take to get to the moon?
Oh, the full month. So the thruster is firing the whole time until you get there. So which is different from the chemical thruster, which fires at the beginning, right? It puts you in a transfer orbit, and then you fire when you get there to get into orbit, or something like that. But in this case, the thrust is very weak compared to chemical thrusters. So you fire the whole time. And instead of taking, if you go with chemical thrusters, it's about 1 week transit. And it will take you on the order of 1 month, 2 months to get if you use electric propulsion. But if you're not in no rush, that's probably okay. You can take the summer off and come back when you're at the moon, right? Yeah.
So what's the approximate power of a single one of those little thrusters?
About 1 watt.
How much?
1 watt.
1 watt.
It's very small, right? Yeah.
Considering how small the thrusters per one of those, do you think it'll ever get to the point where we can use one of those kind of thrusters actually put like a manned mission to space? Like,
I didn't even mention that, absolutely. That's a very good question. If these are so good, can we use them for other missions, like, crewed missions into space, human missions? And I think we can. Remember, we have these big devices. Potentially, we can use these for those missions. This can handle thousands of watts, right? The big siblings of these plasma thrusters can handle up to hundreds of kilowatts of power. We have about 1 watt on one of these. If we put a little bit more tips, maybe we can handle 10 watts per chip. But if you put many of them, you can get to those power levels in no time with really good performance, actually better performance than traditional plasma thrusters. So yes, that's probably what is next, what we call the densification of this technology. And it is so small that in principle you can carry many of them to your mission, many more than the ones that you actually need, just in case you need extra propulsion, right? Well, that's a very good question. Yes?
The other question was, how did you said that the fuel was already on the ship. Where does the power come from?
The power comes from an electronics board and the solar cells that are feeding it, right? So, for example, this guy, you see there are a few boards beneath the thrusters. Those are the electronic boards that process the power and handle the switching and has a little computer that controls how to fire these things. And the power comes from the satellite. It has its solar arrays, a little power converter in here that distributes the power to all the subsystems and the propulsion too.
Can you like feel the ions coming off, or is it like dangerous or anything if you put your hand next to it?
You probably don't want to do it because they only work in vacuum. Now, if you have a spacesuit and try to do it, you probably won't feel it. The thrust of one of these devices is equivalent to the weight of the antenna of a mosquito, which you probably wouldn't feel, right? This is the magic of these technologies. They're very weak, but they fire for very long times. So in the long run, you travel faster than using chemical thruster. Yeah?
So you mentioned you sold the technology to government agencies. Why haven't you sold it to private companies or telecom companies?
Well, there has been, there is a research agreement with the government, as many other research agreements with the government, to perform research to develop the technology, right? And my students, my PhD students who graduated about 3 years ago, founded a company already, and they are commercializing the technology. So the idea is to make this available for the whole world, right? Yes?
Is there any kind of like decay on the thrusters? Like, do they actually wear out?
Yes, absolutely. There are several decay mechanisms. You can, for example, hit the grid, and the grid can be eroded because of the high energy of these ions. The liquid can decay, for example, if there are electrical discharges, like little sparks. So these are engineering challenges that we have to work and to prolong the life, to extend the life of these devices. Yeah.
Is there any potential for refill in space?
Oh, that's a very good idea. Yeah, we do it on the ground. Right, so many times when the thrusters are still good, if these life-limiting mechanisms haven't acted and we run out of propellant, we can literally put more propellant and fire them again. So in space, I would say why not? In fact, it's easier to transport fluids that have zero vapor pressures in space than it is, for example, liquid hydrogen, which is very volatile, or water, right, which is not only volatile but freezes very easily when evaporates in space. So in this case, yeah, that's a very good idea. We should do it. Maybe we can plan a mission like that, right? Having a Cubesat, sending a Cubesat with empty tanks, sending another one with a refill, and go there, refill it, and there you go. Something like that. It's a very good idea. Have to propose that.
So when you said it's got the power of those volts, how much power and what rating batteries do you need to fire your rockets for 500 hours?
Well, the batteries are recharged the whole time, right? So the instantaneous power that we need is on the order of 4 or 5 watts, and the mass of these batteries are a few hundreds of grams. So it's not very large. All of this is a very small devices. Yeah.
How long do they last before they?
Well, the tank is designed for 500 hours. We can refill, and the thrusters themselves will die. Right now, our current design will die at about 500 to 600 hours. Right. But you know, that this is also part of research. Our goal is to extend the lifetime to thousands of hours, which is the lifetime of the big devices. Yeah. Other questions? Yeah, one more.
Do the thrusters release heat from their power?
Oh, that's an excellent question. Actually, these are very cool, not because they look cool, because they also run cool. They run cold. You know, typical, obviously a chemical rocket is going to run hot because you're burning stuff. A plasma thruster like this, it runs at very low density, but hundreds of thousands of degrees. It's also very thermal. But this process that I show you with a very strong electric field, that happens at room temperature. And actually, all the energy is contained on the molecules themselves. And when they leave, they take this energy with them. So the engines become cooler because it's an ion evaporation process. And if you think about cooling mechanisms, for example, in your body, when you want to cool down, you sweat and you have evaporation cooling, right? So the water of your body leaves, which is the hottest part of your body, and then you cool down. So it's very similar to this. If anything, we actually cool down. We don't heat up. Right. Oh, there's another one here.
So you said that so since these produce like very little power, but it's like for very long times, so exponentially the sort of like the velocity of the spacecraft will exponentially increase. So you mentioned that like the satellite would like say intercept a near Earth object. So you have to like slow down in order to like, go to the object. So would that mean like you have to think about like a long period of slowing down, or?
That's a very good question. And this is an orbital problem, right? So what we're doing in that particular problem is we're matching the orbit of the asteroid. It's not that we're zooming in like a bullet, right? So we're matching the velocity of the object, and when we arrive to it, we arrive with very little excess velocity. I mean, this is by design. So you arrive with a few meters per second excess velocity. You arrive very slowly already. And the gravity field of the asteroid is so small that actually you can get into orbit around it. And you can actually descend on the asteroid, touch down, and take off with these little thrusters. Because a satellite that, you know, with this small on an asteroid that is also very small will produce a gravity that is 1,000,000 times weaker than the Earth's, for example. And then you can take off, actually. Very good question.
Okay, so that was the last. I'm looking for 3 volunteers, one from each class. From race car. Just coming down. One from Cowboys. One down. And one from UAV. Since our tradition, we actually present our speaker with our wonderful, cool-looking t-shirts. So, I would like you to present t-shirts together. So you can just.
Oh, excellent.
Say thank you.
Thank you so much. Okay. Thank you. Thank you.